Hi, and welcome to Engineer's Mindset. Today I'll be taking us through three-dimensional force analysis, also known as spatial force. A force is said to be a three-dimensional force if it has components in both the x, y, and z. That is to say, the force occurs in space. For instance, let's say I have a force here of force F. Okay, let's say the direction of this force to the x is simply theta x. The angle it makes to the x is theta s, and the angle it makes to the y is theta y. Similarly, if this force occurs here, it means the angle it makes to the z is going to be what? Theta z. So let's have this. Okay, as established when we were talking about two-dimensional analysis, I told us that these angles, theta, represent what? The direction of force. So theta s represents the direction of this force in the s component, theta y represents the direction of the force in the y component, theta z represents the direction of the force in the z component. Alright, now to find the s component force, as explained earlier, s component force will simply be what? If I hold the tip of the arrow and pull it to the x, it goes through this angle theta x and it points towards the right, so it's always positive. The same thing happens if I hold the tip of the arrow and pull it to y, and the same thing will definitely happen if I pull it to z. Okay, now the force component in the x, let's use fs to represent it. Force component in s is simply what? Force times cosine of the angle it makes to the x. So we'll have f cos theta s. The force component to the y, let's use fy to represent, is also going to be f cos theta y, and therefore the force component to the z will be f cos theta z. So these are the first three formulas you need to know. Force component to the x, f cos theta x; for y, f cos theta y; and for z, f cos theta z. Now if I take the resultant force in vector form, resultant force will be, now remember that I told us earlier when we were doing two-dimensional analysis that x in vector form is usually what? I direction, while the y is usually the j direction, and then the z will definitely be the k direction. Okay, so in vector form, resultant force fr will be, okay, fxi plus fyj plus fzk in vector form. Okay, so it means the resultant force in vector form is now equal to, we know what fx is. F is simply the force times cosine of theta x, so this is f cos theta xi, okay, plus fy is f cos theta yj, okay, plus fz is f cos theta zk. Okay, if we have this, alright, so resultant force is now equal to, f is common between the three, so you can simply pick out f into f is common, so pick out f. So we have cos theta x I plus cos theta y j plus cos theta z. Okay, so we have this. Okay, so it means now that we can write this equation as, we can simply rewrite this equation as saying that resultant force is simply f times lambda, okay, where lambda is what? Cos theta x I plus cos theta y j plus cos theta z. Okay, this will give us lambda. So lambda stands for what? Unit vector. Okay, lambda stands for what is called the unit vector. Okay, all right, y cos theta xi. Okay, so cos theta yj and cos theta zk represents what? Lambda. All right, so we have this. So this other formula we should pay attention to first. Pay attention to this, called this equation 1, and secondly pay attention to this other formula that for forces acting in 3 dimensions, the resultant force is simply the magnitude of the force times the unit vectors. Okay, so lambda is unit vectors. Now unit vector signifies the direction of force. So it's not in all cases that unit vectors has to do with what? The angles. It's not in all cases that unit vectors has to do with the angles. So in most cases it has to do with position. It indicates the position and direction of force. That's what unit vector stands for. So when it has to do with position, in terms of position, okay, in terms of position, the unit vector becomes, let's say we have point A and B, or let's say we have position A and position B. Okay, so lambda, which is a unit vector, becomes the difference in position arrow AB all over the magnitude of the position vector arrow AB. Okay, this is what we define for unit vectors, where this arrow AB, which is the position vector, is usually what? Arrow B minus arrow A. Okay, while this arrow AB magnitude is simply the square root of arrow B squared or arrow A squared plus arrow B squared, and so forth. Okay, so in terms of position, our force is equal to what? The resultant force is equal to magnitude of the force times unit vectors. Okay, and this unit vector, okay, and the unit vector will now be, this is now force times what? Position vector arrow AB all over magnitude of the position vector arrow AB magnitude. So this could also represent what? Our force in terms of position, in terms of positions. Yeah. All right, so we said earlier that in vector form, resultant force is simply Fxi plus Fyj plus Fzk. Okay, so this is in vector form. All right, so to obtain the resultant force in magnitude, okay, okay, Fr is simply what? The square root of Fx all squared plus Fy, just like we did in 2 dimensions, all squared plus Fc all squared. So this will give us the resultant force in magnitude. Okay, now these are the key formulas you need to bear in mind in 3 dimensions. The first formula is that force in the x-axis is simply force cos theta x, force in the y-axis is simply force cos theta y, and force in the z is simply force cos theta z. Okay, noting all this in vector form, this is resultant force. Okay, and we can be able to break that equation down to what? Obtaining that the force is simply what? Magnitude of the force times unit vectors, and unit vector represents what? Cos theta x, cos theta y, and cos theta g. Okay, knowing that, we also said that we can find the unit vector in terms of position when it has to do with between 2 points A and B, or let's say different positions, that the unit vector has to do with the position vector divided by the magnitude of the position vector. Okay, so position vector is simply arrow B minus arrow A, and then we'll have this. Okay, all right, we are going to be applying this in relevant calculations in 3 dimensions. We'll start our calculation in the next videos. All right, so I will see you in the next videos. Please like the video if you find it interesting, share to your friends for more subscribers, and comment in the comment section if you have any question to ask. Thank you. I'll see you in the next video.